So let me introduce Professor Rudin. So she kindly accepted our invitation. So Professor Cynthia Rudin is a professor of computer science and electrical and computer engineering, statistical science and biostatistics and bioinformatics at Duke University, where she directs the Interpretable Machine Learning Lab. She has published numerous papers on interpretable machine learning. So if you're in the field, the chances are that you know her already. She has won several awards. I'm not gonna mention all. And she has been named by BusinessInsider.com as one of the 12 most impressive professors at MIT in 2015. Her work has been featured in news outlets including New York Times, Washington Post, Wall Street Journal, Boston Globe, Business Week, and NPR. And today we have the distinct privilege of having Professor Rudin present for us. And for that, without further ado, I leave the floor to Professor Rudin. Thank you very much for accepting the invitation.
Sure, my pleasure. So I'm going to talk about something, I know it's not exactly along the lines of the workshop theme, but I think you're going to like it. So the title of the talk is We Turn to Black Box and Do a Scientific Discovery and an Interpretable Model, a Study in Predicting Breast Cancer Years in Advance. Let's think about this storyline. So let's say you take a black box. It holds some really important, beautiful secret about the world. You open it up, reveal what it is, turn it into an interpretable model that really leverages this knowledge to make the world a better place, right? That's the story. It's so cool when this happened, and I feel really lucky to be able to tell you about this case where this happened recently. It's a really cool medical discovery published in 2024. It's on the topic of computer-aided mammography. All right, so I'm going to discuss two papers. The first one is on interpretable deep learning with prototypes. You can use it for any type of data. It was published a few years ago in Nature Machine Intelligence. And then the second one, where the big discovery is, was published in Radiology this year. And my collaborators on these, I have several wonderful collaborators: Alina Barnett, Feed Schwartz, Joseph Lowe, John Donnelly, and Luke Moffett. All right, so I want to start with this question. So we're working on breast biopsies, and I have put here a picture of a breast lesion, and I need to decide whether to biopsy it. Okay, so if I was using a black box, the black box would say the probability of malignancy is low, I predict benign, and I'm not going to tell you the reason because I'm a black box and I don't do that. Okay, instead, let me switch to a saliency map approach. So here it would say probability of malignancy is low, predict benign. And the reason is because I'm looking right here, right at the lesion. Great. I already knew where the lesion was. That's why I sent this image into the algorithm in the first place. So this doesn't tell me anything I didn't know before. So let me show you instead the approach that we're taking, which uses case-based reasoning. So this is our algorithm. It's called the Interpretable AI Algorithm for Breast Lesions, so IAIABL. And the algorithm dissects each part of the image and relates each part to a set of prototypes. Okay, so this part of the image looks like this part of this image. This is in my training set. It has an indistinct margin. So I think maybe, this part of the image looks like it has an indistinct margin. Okay, whereas this part of the image, that looks circumscribed. It looks like this part of this circumscribed margin lesion. This one's in my training set. And then I can assign points for each of these comparisons. Like this looks like that, this looks like that. I would get half a point on the malignancy score because indistinct margins are bad. Circumscribed margins are good. So here I would subtract some points from the malignancy score. Okay. Then I can say, okay, probability of malignancy is low, predict benign. Why? Because the math primarily has a circumscribed margin. Okay, so the thing is, you don't have to trust this. You can argue with it. You can decide when not to trust it because you can see its reasoning process and it's completely faithful. Okay, and that's the nice thing about it, that you don't have to trust it. It's all done with interpretable deep learning, which picks out these which prototypes to compare to and how to do this comparison on the subset of these images. So I'm going to spend a few minutes just tell you how this type of neural network operates. Okay, so this network uses case-based reasoning. It's not the same thing as in the previous talk where you had a prototype that was like the center of like a bunch of points in the latent space, because that doesn't correspond to like an actual training example. Here, my prototypes correspond to actual parts of actual training examples that are chosen to be prototypical representatives of the class. So let me show you an example on a bird data set to make it clearer. So this is the network explaining to me why this bird looks like a clay-colored sparrow. And the network is going to pick out different parts of this bird. It's highlighted in two different ways here. It's like saying, okay, why is that bird like classified as a clay-colored sparrow? Because this part of the bird, right, highlighted in two different ways, looks like this part of that bird. And this is a prototypical clay-colored sparrow. Whereas this part of the bird looks like this part of that bird. And this is a prototypical clay-colored sparrow from my training set, okay? So the network here is, you know, making all of these comparisons. It's actually computing a score for each comparison. And it's saying, this looks like that, this looks like that, this looks like that, this looks like that. So we decided to call our paper, This Looks Like That. And the nice thing about this network is that every step of it can either be checked by a human visually, like this looks like that, or it's just adding up a bunch of numbers. Okay, so what this thing does is it starts you off with your favorite convolutional black box, you know, convolutional neural network, and it adds a prototype layer to the black box just before the last fully connected layer. And that forces the network to do this kind of case-based reasoning. And the prototypes are learned during training. So I want to show you this in more detail about how the computation works, okay? So you start with your favorite black box. You got convolutional layers and then a fully connected layer at the end, okay? Standard black box convolutional neural network. And then you just add a prototype layer just before the last fully connected layer and just retrain it, or keep training it, I should say. And this prototype layer, you know, does the comparison. It just it scans the image. You scan the image looking for parts of the image that look like each of the prototypes for each of the classes. So his class 1, class 2, class 3, and so on. Okay, and the prototypes, like I said, they're learned during training, and I'll show you how to do that in a minute. So let me show you a little bit more computation, kind of like, I just want to show you the numbers for this whole computation using an example. Okay, so why is this bird classified as a red-bellied woodpecker? Because the network thinks that this part of the bird looks like this part of this bird. And there are two numbers that come with that comparison. One is how similar this is to that, which is this number here. And by the way, this looks very much like that. I don't know if you can tell, but it's like an orange circular thing, well, C-shaped thing with like a white C-shaped thing and like a black thing. So these are very similar to each other. So I get this number, which does that comparison. And then this number over here is the class connection weight. It tells you how important this bird is for representing this red-bellied woodpecker class. So you get just these two numbers for each comparison. And then if we have 20 prototypes per class, we get 20 numbers, we add them up, and that's it. Okay, so that's the computation you do for each class. Okay, so let me just show you just a little bit more of that computation there. So here we got 32 points for this red-bellied woodpecker class. For the next highest rated class, which is the red-cocketed woodpecker, then we didn't get as many points, but maybe it's because red-cocketed woodpeckers don't seem to have red heads, and so it can't get really any points by doing the comparison on the head, but it does have similar feathers, so you can see the comparison there on the feathers, okay? All right, so here's an interesting one, because this particular bird, so this was classified as a Wilson's warbler. It was correctly classified as a Wilson's warbler. It is a Wilson's warbler, but it doesn't really look like a Wilson's warbler because Wilson's warblers have black spots on the top of their heads, whereas this one doesn't. I think maybe it's a baby. So the network is doing a very careful job kind of avoiding the top of the bird's head and looking at the placement of the eyes and the beak and so on, and that's how it's doing its classifications. And if it, you know, it actually does look like another class too. So there's a class called prothonotary warbler, but it doesn't quite get as many points, even though these birds don't have a black spot on the top of their head. So it's really neat. Now, the way let's just talk about how it's trained here. So it's trained by solving a minimization problem over the weights and the choice of prototypes, okay? So the first term is a standard cross-entropy loss term for making the predictions accurate. Here, the predictions depend on both the weights and the prototypes, so that's why I colored it both green and purple. And then there's a term that keeps each prototype close to its correct class, and another term that keeps the prototypes far from the wrong class. And this creates a kind of clusteriness to the latent space. Now, the last term is a fine annotation loss, which teaches the algorithm to look at the right spot in an image so that it won't be confounded. We don't use this for bird classification, but it's really helpful when we're working with small medical imaging data sets, because without it, you might have confounding where the network is looking in the wrong place. And then when you put this in, then the network knows where to look. And we use a form of alternating minimization between the gradient steps for the whole network and for the prototypes, for the projection steps for the prototypes. So the prototypes get to wander around the latent space, and then we have these projection steps that snaps the prototypes to the nearest training examples, so that the prototypes are always training examples. And that's how it works. Now, our method, since it was published in 2019, has become very popular. The paper has over 1,000 citations, and people appreciate that it tends to have the same accuracy as the black box algorithms. So they use it for all kinds of stuff now, and people build on it to create lots of variations on it too. These are papers where we don't know the authors personally, and they're using it for cool things like chest radiography and earth imaging and skin cancer detection. It's just really kind of cool what people have done with it. All right, so we decided to use this tool for mammography. Mammography is important because breast cancer is the most commonly diagnosed cancer worldwide. Mammography is the hardest task in all of radiology. Radiologists miss a fifth of breast cancers, and up to 3/4 of biopsies come back as benign, in other words, potentially unnecessary surgeries. So breast cancer is so common that in the United States, every woman over 40 has to get a mammogram every year. So if you care about people, you care about breast cancer. All right, so now using our interpretable neural networks, we can show the radiologist information that might help them reason about an image. So I showed you this example before. I'm going to show you a couple other examples so you get more of a sense of it. So it's kind of showing the whole reasoning process here. So it's saying this part of the image here, this is the lesion. This part of the image, the margins around the lesion, look like, this circumscribed margin class, right? So this is an example of comparisons with the circumscribed margin class. And so there it is classifying circumscribed margins. Circumscribed margins are not so dangerous. Spiculated margins are very dangerous. You don't want to have spiculated margins. So this is an example where it's doing the comparisons for the spiculated margin class. So having this kind of algorithm, it's like super helpful for troubleshooting because we can figure out how to augment the data set or adjust the model if something goes wrong. So for instance, we've been able to eliminate prototypes that were confounded. And the method is quite useful for medical imaging beyond mammography as well. So we applied the same technique to analyze EEG signals of patients that are in the intensive care unit, and their brains are being monitored because they might get a seizure that might destroy part of their brain. Seizures are quite dangerous, so doctors really monitor these patients carefully. And this paper is just about to be accepted in the New England Journal of Medicine AI. And I just want to show you what we're doing here. So this is a snapshot of the interface that we built for this. So down here, this is the EEG signal that we're analyzing from the patient's brain. These are the prototypes that are similar to this signal that the neural network found. And then this thing here, this strange object here, is a projection of the last layer of the network that's classifying various types of EEG signals. So each of these tentacles is like a different type of EEG signal. And we've been trying to figure out what this thing looks like for a while now. We think it may be some kind of funky fish. Anyway, you can really look at this thing and see how the patient's brain is changing over time. It's really cool because you can see this wandering around on this strange fish. And it's all case-based reasoning, all interpretable neural networks. And one important thing I should tell you is that all the models I'm showing you were compared to black box models. The models for mammography, for EEG, and so on, and for bird classification, and they perform as well as the black boxes. There's no sacrifice of performance for interpretability. All right, so let's talk about whether we can go beyond, beyond what I just spoke about and talk about actually making scientific discoveries, right? Actually helping humans gain medical knowledge with interpretable and explainable AI, okay? So a few years ago, I was given a talk over Zoom on the stuff that I just gave, right? And it was on interpretable mammography. My friend Regina was at that talk. So Regina is a famous machine learning researcher. She just won a MacArthur Genius Award, so she's very well known. And she's also a breast cancer survivor and one of the reasons I got into this in the first place. And Regina's my good friend, but she's also sometimes sort of like painfully honest. And, I appreciate that. So she listened to my talk on the work I just presented to you, and she said, well, that's all well and good, but that won't solve my problem. She said, for my problem, you still need a black box. So I said, Regina, what's your problem? And she said, well, I want to predict breast cancer from mammograms up to 5 years in advance. Your thing might help when the lesion's already there and I want to detect it. But I want to predict this stuff way in advance, like before the lesion even exists. And indeed, she has a paper in Radiology where she does exactly this. It predicts breast cancer up to 5 years in advance. It was trained on 44,000 exams. Okay, so nice big data set. And it's surprisingly accurate, shockingly accurate, if you ask me. Right here are the AUCs for predicting in advance: 1 year, 2 year, 3 year, 4 year, 5 year. 0.71, right? So, and you want to keep in mind, you want to read this keeping in mind that random guessing is 0.5, right? And perfect is 0.1. So these are way better than random guessing. But Regina says it's a complete black box, right? Nobody knows what it's doing. Even the doctors don't know what it's doing. And this is a task that doctors don't do, by the way. They don't look at a mammogram and predict breast cancer 3 to 5 years in advance. And I thought, oh man, this is a bad one, right? Even Regina, who is a super smart, top-notch AI researcher and a breast cancer survivor and the creator of this powerful model, along with her student Adam Yala, right? They didn't figure this one out. Should we even try this? And again, to remind you, just breast cancer is really common, and there's a huge amount of data because like all women over 40 get mammograms at least once a year. So there's been tons and tons of data generated over decades, and yet there is not a single risk prediction tool, machine learning or not, for predicting longer-term risk from mammograms, right? Radiologists don't do this. So the fact that their method, Mirai, was able to do this was amazing. And nobody knew how it worked, right? And it's designed in a way that is completely impenetrable. So this is the architecture from their paper. So there's a bunch of convolutional layers, and then there's a transformer. If you think about CNN, I'm kind of okay with CNN. CNN is like iterative summarization. It's like reading a book where you summarize each page, then you take the page summaries to summarize each chapter, then you summarize the chapters into units, and then you draw a conclusion from that, right? That's okay. That's not too bad. But then they put the output of the convolutional layers into a transformer, right? Transformers are a total mess. They're like taking the pages of the book and then blending them into a smoothie or something, right? You just can't disentangle where anything came from. So I thought, oh, yeah, this is going to be impossible to figure out. Thank goodness I was wrong. So we actually stumbled onto the answer to this within the first week we were trying to figure it out. And I thought we'd need a ton of fancy tools, XAI, whatever, to explain the inner workings of the black box, but we actually didn't need any of that. It was so crazy simple. So here's what happened. So in mammography, there are 4 images taken, 2 of the right side and 2 of the left side. Mirai takes all 4 images as input and produces a magical risk score from this black box that nobody understood. But we, unfortunately, or fortunately for us, didn't have the right data to do this, because a lot of our data was from a database where we had only one side. And it's because the publicly available part of the in-breast data set has a lot of mastectomy patients. So they only actually have one side. So we couldn't send it into Mirai at all. We just could do nothing. So how are we going to investigate this if we can't even send anything into the algorithm? So I said to the students, okay, you know, let's just replicate the left side as if it were the right side, right? There's nothing inherently different about the right breast as compared to the left breast. So it should be fine to replicate it and just send it into Mirai. It won't know the difference. But as soon as we did this, Mirai broke. So what happened was, this is for the in-breast data set with 120 patients here, where we mirrored the left side, okay? And then some of these images actually had lesions in them. So these patients were clearly not low risk, okay? So the original risk scores were like upwards of 0.6, 0.8, whatever, 0.468. And yeah, some of these patients, like I said, they actually had lesions in them, so they were not low risk. But then as soon as we replicated the left side to the right side, then everybody was low risk, okay? So Mirai's risk scores went upwards from 0.6 to 0.8 down to 0.2. So we thought, whoa, symmetry. I mean, symmetry has got to be the key to this whole thing, because if Mirai can't tell that a breast with a visible lesion in it is high risk when you replicate it to the other side, then this model has got to be using symmetry. So we had a conversation with our radiologists, and they told us that indeed they do go back and forth between the two sides to see what's normal and what's not when they're detecting breast cancer. I mean, they don't predict breast cancer, but they do kind of look at both sides when they're detecting it. So in other words, interestingly, asymmetry is something doctors look at to verify that cancer exists as part of a standard calculation that they do. But now we know that there are these broader, subtle asymmetries that we can now check to predict cancer in the future, even when there is no lesion at all. So just to show you, patients look very different from one to the other, right? They look very different between patients, but they look similar between sides. So that's why this approach seems reasonable. So we said, fine, you want to use symmetry? Then we'll make it so all you get to use is symmetry. So what we did was we kept Mirai's convolutional layers and ditched the super black box transformer, and in its place we put something much simpler, which is a symmetry detector. It's literally a comparison between the left and the right sides. And our model is called ASYM-Mirai. So here it is. Let me just zoom in on it so you can see that all we're doing is just comparing the left and the right sides. Okay, so it compares the left and the right sides of the CC view and the MLO view, the two views you get of the breast. And it finds the spot where they're the most different for both, for both views. And then it just calculates how different those two spots are in the latent space, and then averages the two numbers from the CC and the MLO views, and that just gives you a risk value. And that's it. It's just averaging two numbers. No black box transformer, just averaging two numbers. So you just summarize and compare the left and the right sides. And this much simpler thing actually performs almost as well as Mirai. Not 100% as well, but really, really close. So in terms of performance, very, very similar. So these are the ROC curves. This is year 1, 2, 3, 4, and 5 for Mirai. This is for ASYM-Mirai. And so you can see that's very, very similar. Okay, so yeah, but the cool thing is, so ASYM-Mirai is much more interpretable, right? Not only can it tell you that there's a risk, it can tell you exactly why. It can point to exactly where on the two sides the asymmetry is. So Mirai, right, it just gives you a number, just gives you a risk, and that's it. So ASYM-Mirai tells you that 1, it found an asymmetry, which is why you're higher risk, and 2, where that asymmetry is. It's right here, you see? All right, so because we know what ASYM-Mirai is doing, we can figure out when it's confounded and when it's not. So here's a case where ASYM-Mirai said that this thing was somewhat risky, but if you look at what it's doing, you can't trust it, because the patient had an implant on one side, and that's messing up the symmetry, right? Mirai probably messed this one up too, but you wouldn't be able to check that. And then here's another case where ASYM-Mirai says high risk, and there's an implant on one side, but ASYM-Mirai was not fooled by the implant this time. It's actually not confounded, and you can see that because it's looking at this spot over here where there's an asymmetry that's real. And then here's a case where the images are misaligned. We're busy fixing the alignment now, but this is before we fix the alignment. XAI-SA gave this one a moderate risk score. Mirai gave it a high risk score. You shouldn't believe it, and now we know why. And then here's a case where the patient had some pronounced lymph nodes. So if you didn't know what it was doing, you might think it was looking at those, but in fact, it wasn't fooled by that at all. It was looking at something much more concerning over here. Okay. Now, one really interesting thing we found is that location consistency matters. So if the location of the box, which is your sort of maximum asymmetry box, is in the same place every year, so if this box is really consistently in the same place every year, and you're low risk, then you might be special. Because if you're low risk every year and that window stays where it is, you might be in a very low risk group. So we're looking now in a more detailed way at this group of patients because it might mean that they could potentially get mammograms less often without compromising safety. So here's one of the results from the location consistency analysis. So we take these 59 patients who are the most consistent in terms of their maximum asymmetry windows, and we rank them by risk according to XAI-SA. 5 of those patients got cancer, and those 5 were ranked among the riskiest by XAI-SA, right? The high AUC means that we can predict cancer much better for those patients than for the general population. And so we can compare this to what happens if we put all the patients up there. So here, here the location consistency ROC curve is up here, and then this is if we tolerate less consistency, and then until we get the whole data set down to here. And the prediction ability is still good, but it's not nearly as high as for this guy, okay? So you can really see that this subgroup that we've identified might really be special. All right, so those are the topics that I wanted to discuss today. And I just want to finish up with some lessons learned. Okay, so first, our work on symmetry owed a lot to Mirai, right? If Regina and her student had not made the code for Mirai public, we couldn't have done this. And we also, just so you know, we did run into problems obtaining data. So data is actually a real struggle with medical data sets are very difficult to obtain. I really wish there was more public data sets because, you know, it really affects public health if such data sets are available. And second, I have not seen a trade-off between accuracy and interpretability. I've yet to find a problem where I actually needed to explain a black box model. You know, I've personally never used XAI techniques for anything. We've always been able to create an interpretable model that was as accurate as a black box. And even for this case where there was this black box and nobody knew how it worked, we still didn't use XAI techniques. So I personally haven't seen the use for them. We've always been able to build inherently interpretable models. And we've not seen a trade-off between accuracy and interpretability. Right? People say there's a trade-off, but everywhere we've looked, we've seen evidence to the contrary. And then finally, you know, it's possible for AI to help us gain new scientific knowledge, right? Before we did this study, it was known that symmetry was useful for analyzing current risk, but not for predicting 5 years into the future. So this is a new piece of knowledge that we gained. Yeah, and so that's it. That's the end of the talk. Thank you very much.
So, questions?
Hi, thank you very much for the talk. So I'm trying to wrap my mind around it, but I just haven't thought through. So I'm curious about, in terms of data scale and the requirements of labeling the data, what's your opinion and take in terms of the interpretable machine learning deep learning models? And I was imagining maybe you need more well-labeled data, but maybe in the future, if it's interpretable data, it actually has less requirements on the scale of data set.
Oh, well, we haven't found that at all. Everywhere that the regular black box models work, the proto-peanuts work as well. So we haven't found any cases where they don't perform as well as the black boxes when they're fully trained. And then, I mean, it is more difficult to train them, but when you do train them properly, then we haven't found any need for extra labeling. The one thing you do need, though, once you start using these interpretable models, obviously, interpretable models have interpretable flaws. So black box models have flaws that are invisible. Whereas when you start doing interpretable models, you're like, oh crap, I gotta fix this. And then you have to start labeling. So we always compare to black boxes that we know are confounded, whereas we don't allow ourselves to be confounded. So then we have to do extra labeling and stuff like that just to make sure it's not confounded.
Thanks. It was a very interesting talk. All of the examples that you showed seemed to show a small contiguous patch as being the sort of thing that, I've identified a small contiguous patch of the input as being the thing that allows for interpretability. I'm wondering whether you've run into situations where what it seems to be learning from or basing its decisions on are not small contiguous patches, but maybe something distributed, something that maybe isn't quite so visually obvious. Have you run into a thing like that?
Yeah, I mean, so I do a lot of work on wearable devices on PBG signals, which maybe would have been more appropriate for this audience, but I couldn't resist giving the talk on mammography, and I don't have a talk prepared on the PBG signals. But in that case, what we've been able to do is find a sparse basis for the signals and represent the new signals in the sparse basis. So that's one way to get interpretability. And another way to do it is to do something like concept whitening, where you take the latent space and you force it to have certain concepts, the unique information about each concept along the axes. And something like concept whitening is very easy to do. You train your black box, and then it's like one extra pass through the data set with, with the concepts. You have to have a database of each concept. You have to say like, oh, I'm going to put the airplane concept on this axis. So I would show you a bunch of airplanes and you'll use that to form the concept. But if you have that extra data, then you can just put the unique information about each concept along the axes. And then that can have very abstract concepts like texture. In images, you can do texture, you can do color, you can do, I don't know, yeah, whatever you want. You can put them on the axes of the latent space with concept whitening. Yeah, so concept whitening, it's kind of like grandmother nodes, like you think about, you have a node that recognizes your grandmother or something. So the concept whitening method, you've picked out this node is going to handle the unique information about airplane that none of the other nodes are allowed to handle, right? That nobody else is allowed to handle unique airplane information. And so you just have this one axis, which corresponds to the one neuron, one node that handles all the unique information about airplane that goes through the network. It's not a concept bottleneck model. Not really into those, because those you're modeling things unnecessarily. Like we used to call it feature engineering, to be honest. I don't know how that terminology took off, but basically the concept whitening is much softer in the sense that if you're using some unique information about airplane on your way to the final destination, then the amount of airplane information is going to be shown on that axis, or that, the activation of that node, however you want to say it. Does that help?
Yep. So yeah,
Okay.
person who asked the question, yes, thank you. So we have time for more questions, actually.
Yeah, thank you for the very nice presentation. I just wanted to ask a clarification about when you're trying to predict the cancer likelihood in 5 years. Are you only looking at the asymmetry in asymmetry 5 years prior, or are you looking at it through the years? Like I didn't understand that. So are you just giving it the left?
It's just one signal. So you just get a mammogram at one point in time, 4 images, send it through the thing. To find that special subgroup, then we were looking over time to see if you're low risk over time and if your symmetry window is in the same spot.
Ah, okay.
Mhm.
Cool, thanks.
Sure.
Thank you very much for the presentation. It was really interesting to see the result of Mirai and the high impact of the symmetry that has in the prediction. But yeah, there was this gap in performance, like maybe 5% or something like this with the black box transformer model. So I was interested, do you think there are other factors that also help the prediction apart from the symmetry? And in that case, how could you identify these factors and also make them interpretable in a way?
So the problem, I think the reason for that gap is because we didn't have the data to train XAI Mirai. We used the convolutional layers directly from Mirai, and we weren't able to train them because we didn't have access to their gigantic data set. So we actually couldn't train them at all. So that could easily explain the gap. Like literally, we took the trained weights for the CNN layers of Mirai and then trained our own symmetry detector. Like literally, that was it. So that's the 5% gap right there. I can tell you that. I would love to be able to get access to some data to be able to actually, train the weights so that we're globally optimizing. But yeah, like I said, it's really hard to get medical data.
Okay, thank you very much.
Mhm.
Thank you for the interesting talk. I have a question about supervision. Do we have like reports of doctors so we can use more supervision than just labels, maybe text, and that will guide maybe the black box model to be more interpretable?
So I don't think it'll make the black box model more interpretable, but I think what you can do. Okay, so okay, let me that question there's a lot of ways I could interpret that question. I'm not sure which way to do it. So let me interpret it one way and then I'll interpret it another way. Okay, so for the first part of the talk with ProtoPNet, with the IAI-BL thing, we actually do use the doctor's notes to figure out whether it's circumscribed or whatever, like the different margin types. And then we were also using the doctors to actually label some of the images for us, like where are you looking in this image, so that our attention is in the right place for that to train that last term in the model. What we don't have are things like age, which is actually quite a useful predictor, and like ethnic background. There's certain ethnicities where there's a higher risk. So those things could be kind of useful if we had those. We just didn't have them. For the Mirai stuff, nobody predicts breast cancer 5 years into the future, so doctor's notes would not be helpful there.
Thank you very much.
Are there more questions? We have time for one more question.
Thanks for the wonderful talk. I want to ask the first part of the presentation, talk about the bird classification. You showed many examples where the explanations are really reasonable. I'm wondering whether you have incorrectly classified samples, how the explanation would be. Would it be inconsistent with each other, or they are highly confident about the wrong explanation? Thank you. Okay, so you can have all of the above, or any combination of the above. Let me show you a case where it was wrong. Let's see if I can grab this. Okay, so share that. Okay, so this is a case where I got it wrong. So in the case I showed you earlier, the base model was a VGG 16, and you can use ProtoPNet with any base model. So if we change it to DenseNet 161, it actually gets it wrong. And I can show you here, I can show you why. So what happened here was, again, this bird is I think it might be a baby Wilson's warbler because it doesn't have that black thing on the top of its head. And so the network actually really thought it looked like this prothonotary warbler. Sorry, I'm like, that looks really very much like it. No, this prothonotary warbler. So it actually it actually got it wrong. So here's a case where it gathered evidence based on like the colors and so on and so forth, and it actually got it wrong. Whereas this would have been the correct answer, and it just couldn't use the top of the head, you know, to get evidence because this bird doesn't have black on the top of its head. So what you can do when you see this is you can say, oh, look, it's avoiding the top of its head. I need to add more baby Wilson's warblers into this data set so that I don't mess this up anymore. And then other things that can happen, sometimes the prototypes can be like water. So for example, if you're detecting water birds, the prototypes are like water. And you're thinking, oh, you know, this is not good, it's confounded. So then in that case, you can actually manually remove the water prototype so that it won't do comparisons of water to water anymore. So yeah, you get all kinds of stuff, but it's just easier to troubleshoot than if it's just a plain old black box, you know?
All right, so thank you very much, Professor Rudin, once more, and let's give another round of applause.
Thank you. Enjoy your conference. Bye.
Bye. Thank you very much.